All right, in this video we're going to cover section 1.11, which is just a summary of the Unit 1 stuff. You'll notice that this is a very hefty section. There's a lot here, but you may take comfort in the fact that there's not a lot of new information. Most of this is just a review. In fact, that's what this section is designed to do. It's designed to review everything that we've learned in Unit 1. Now, because we're going to be reviewing all of that material from 10 sections, this summary section is going to be fairly long. This lecture is going to be longer than a normal lecture would be. So just a heads up there. We're going to cover a lot of ground, and we'll try to move quickly through the examples, but we're just going to look at a bunch of examples so that we're comfortable with this ahead of your test and everything like that. So the main three things that we talked about in this unit were describing a data set, comparing two data sets, and then describing an individual's relative position within a data set. So we will take some time to review each of those things in turn, and we'll spend the bulk of our time here with this first item. So let's get to it. When describing a data set, there are typically three things that we're interested in describing: the shape, the center, and the spread. And then in addition to those things, we also like to talk about whether or not there are any outliers in the data set and identify those. When we're giving this kind of description, sometimes I'll call this a data profile. Okay, so we're going to practice putting together some data profiles. Let me just remind you of some things that we learned. So first of all, as far as the shape is concerned, what I mean by that is we should first of all identify what type of variable we're dealing with, whether it's categorical or numerical. And then if it's a numerical variable, we're going to want to describe the shape of the distribution. So to do that, we will create a histogram, and based on the histogram, we'll decide whether the data are symmetric or skewed. Okay? So that's what we'll do as far as the shape is concerned. Now, if the data are categorical, then we may still want to make a bar chart, right, to get a sense for what the distribution looks like for that data, but we won't talk about the shape of the distribution so much. Now, once we've identified the shape of the distribution, that will have an effect on the measures that we report for the center and the spread. Okay? For the center, we're going to use the mean if the data are symmetric. We're going to use the median if the data are skewed. And then if the data are categorical, we'll use the mode. For the spread, we will use the standard deviation if the data are symmetric. We'll use the interquartile range if the data are skewed. And we'll use the index of qualitative variation if the data are categorical. So that's how we'll take care of the center and spread. And then finally, as far as outliers are concerned, to identify whether or not we have outliers, we'll compute fences, the lower fence and the upper fence. And that will tell us any values outside of those fences are considered outliers. Now, of course, in Excel, we can just create a box plot, and the outliers will be marked on the box plot with a dot. So that'll be how we identify outliers for numerical data. For categorical data, we don't really have a quantifiable way to identify outliers. Really what we'll do is we'll just kind of look at the frequency distribution that we come up with, or the bar chart that we're looking at, and we'll determine from those things whether or not we have some values that are kind of unusual, in the sense that maybe they just didn't occur very often, right? And then the other thing is that we'll oftentimes when we're dealing with categorical data, in addition to talking about the mode and the IQV, we might also want to look at various proportions, right? We'll take note of unusually large or small proportions within our data set. So I'll give you examples of what I mean by each of these. The chart here on the next page, I think, gives a good summary of what I just said, right? So the measure of center and spread to identify depend on what kind of data you have, right? If you have categorical data, you use the mode and the IQV. If you have numerical data that's skewed, you'll use the median and the IQR. And if you have numerical data that's symmetric, you'll use the mean and the standard deviation. So let's practice. This first example says to provide a data profile for each of the following data sets. So let's do that. This first data set is supposed to represent the density of people per square kilometer for 56 countries. So the first country on the list had 134 people per square kilometer. That was the population density of that country. This country had 57 people per square kilometer, right, and so forth. So let's take a look. We'll open up the data set in Excel and try to come up with a data profile for this. So in Excel, example 1, we're looking at part A, and that's the population density example. So that's this first column over here. Okay, so let's come up with a data profile. Our first order of business is to identify what kind of variable we have. Clearly, this is a numerical variable, okay? And since it's numerical, I'm going to need to decide on its shape. I need to know if this is a symmetric distribution or if it's skewed. And in order to know that, I need to create a histogram. So I'm going to start off by selecting my data, inserting a pivot table, okay. I want the counts, not the sums, and this isn't giving me a very good summary, so I'm going to group into classes. And I'll just use the default setting that Excel wants to go with. I can select this now and insert a bar chart for it, and I can make it a histogram, I guess, by making those bars wider. Okay, we've done this 1,000 times at this point. But there you go. There's our data set. It's most definitely skewed right. So let's write those things down. So I'm going to say the data are, so as far as the shape is concerned, here, let me show you what I'm writing. As far as the shape is concerned, well, first of all, I'm going to say that this is numerical data, and it's skewed right. Okay, now for the center of the distribution, since this is skewed data, I'm going to use the median, okay? And the symbol for the median is a capital M. So let's head back over to Excel to see if we can calculate that. For the spread of the distribution, I'm going to use the IQR, okay, which is Q3 minus Q1. So I'll get those quartiles and the median in Excel, and then we'll come back and write those things down. So for the median, I can just say equals median tab, and then select the data, hit enter. So there's the median, M equals 214.5. For the IQR, I need the quartiles. So for the first quartile, I'll say equals quartile.inc tab, select the data, and I want the first quartile, so I'm going to type in 1. And then I'd want to do the same thing for the third quartile. Select the data, comma 3 for the third quartile. So now I've got those, and if I want the IQR, I can just subtract them, right? So the IQR is going to be this value, well, let's say equals this value minus that value. And there we go. So let's write those things down. So our third quartile was, sorry, I'm just going to write these down and then I'll take you back over to what I'm writing. But the third quartile was 339.5 and the first quartile was 102.25, so that the IQR was 237.25. Okay, so this is what I've written now for the shape, the center, and the spread. Okay. And so that's a pretty good data profile. The only other thing I would need to do is identify whether or not there are any outliers in the data set. And to do that, the best thing to do would be to just look at a box plot in Excel. So let's create a box plot of this data set. I'm going to select it and go to Insert, and under this little histogram looking thing, I'm going to insert a box plot. And sure enough, yeah, it looks like I've got a couple outliers, right? To see what those are, I can add the data labels, and then I can see clearly, okay, so that's 785 and 890, okay? So those are my outliers. So let's write those down. 785 and 890. So those would be some unusual observations. Those are much higher than the rest of the densities, right? Oh, there's one of them right there, right? So this country is very densely populated. It's an outlier, right? It's very dense. And so is the country that has a density of 785. I can't see it in the data set off just looking through it, but those would have very dense populations compared to the normal population density of a typical country. Okay, so there's a data profile. Now, of course, if you were typing up a report or something, you might want to actually include the graphs that we made. You know, pictures speak. A picture is worth 1,000 words, right? That's how the saying goes. So you might want to include the histogram and the box plot. But I'm not gonna make you draw those out here in this space. So we'll just call that good. Let's look at the next one. It says the data below represent the majors of 30 students in a calculus class. Here we clearly have some categorical data, right? These are not numbers; they're just majors, and these are the majors of students in a calculus class. So we want to do the same thing here, identify the shape, center, and spread. The shape, well, it wouldn't really make sense to talk about the shape so much because this is categorical data. So we're not really going to talk about the shape. We could make a bar chart if we wanted to. It might be worthwhile to do that. As far as the center is concerned, since this is categorical data, the measure of center we'll use is the mode. And then as far as the spread is concerned, again, this is categorical data, so for the spread we should use the IQV. And we'll use StatCrunch to compute those things. But the formula for the IQV is K times 1 minus the sum of the sample proportions squared over K minus 1. So this is the formula that we'll use to calculate the IQV. As far as outliers are concerned, since this is a qualitative data set, we don't really have like a mathematical way to determine if there are any outliers. But what we'll do is we'll make a frequency distribution. Actually, what we'll do is we'll make a relative frequency distribution. And if there are any of these majors that are kind of unusual in the sense that not very many people picked that major, then we'll call those outliers. Okay, so let's head over to Excel and play around with this data set a little bit. I'm going to erase all this stuff so that I have room to work. Okay, so I'm dealing with this data set now, the majors. First of all, let's make a relative frequency distribution. So I'm going to select the data and insert to pivot table. Major and major. It's already counting them, which is exactly what I want it to do. It looks like clearly economics is our mode. Okay, it's the thing that repeats the most. But let's get some proportions here. So let's show the values as percent of column total. Okay, so yeah, 43% of people in the class were economics majors, which is kind of an interesting thing. I don't understand why there are so many economics majors in this calculus class. It's not usually the way it goes, but that's okay. So 43% are economics majors. So our mode would be economics, and our modal proportion would be 0.433, or 43.3%. So our mode is economics, and our modal proportion is about 43.3%, or 0.433. Okay, let's go back and calculate the IQV. This is kind of a hassle to do in Excel because it doesn't have a built-in function, but it's better than doing it by hand. So I'm just going to copy and paste my pivot table, and I'm going to paste them as values only. I don't want to paste the whole pivot table. I just want the numbers. Okay, and then I'm going to square each of these. So I'm going to say this equals our proportion squared. And I'll repeat that process for the other categories. Not for the total. Ooh, that's not what I want. I want to do equals this number squared. I don't know why it's doing this. Usually you can just click and drag that little square. And I'll say equals this number squared equals this number squared equals this number squared. Okay, and so now I can add up those values. So here I want to say equals sum, and I'll select these values that I want to add up. Okay, and that's still not quite the IQV. That's just a step in the process, right? That's this chunk of the formula, right? It's the sum of the squared proportions. But now I still need to do k times 1 minus that thing divided by k minus 1. So let's go back and finish it up. The number of categories is k, and that's 1, 2, 3, 4, 5 in this case. So k would equal 5. So let's actually go over to Desmos. I'm going to copy this number so that I can just paste it into Desmos. But I want to do, I'll give myself a little fraction. I want to do k, which is 5, times 1 minus that sum. So I'm going to paste what I got in Excel, and then divide by k minus 1. 5 minus 1. Okay, so there's our IQV. We'll round to 3 decimal places, so we'll say this is about 0.903, or sorry, yeah, 0.903. So I've got my shape, I've got my center, I've got my spread. The only other thing left to do is to determine if we have any outliers. Looking at the data, I would say it is kind of rare to be a math major. I don't know if we would call it an outlier necessarily. Usually something that has less than a 5% chance of occurring would be considered unusual. So this doesn't quite meet that threshold. But it is maybe worth pointing out that, yeah, you know, math majors are a little bit more rare than the other groups. So outliers, we would say, well, math majors only made up about, what percentage was it? They made up about 6.7% of the class. Okay, and you know, whether or not you want to consider that an outlier is somewhat subjective, but I think it's worth kind of pointing out. So that's it for that second example. Let's look at another one. Part C says, a test was administered to a sample of 30 students, and the scores are shown. So the first student got a 13 on the test, and the second student got a 91, and so forth. Okay, let's come up with a data profile. Let me erase these columns. And this is the data for example C, or part C. So I'm going to select the data. This is numerical data, by the way. So as far as the shape is concerned, I'm going to need to make a histogram to determine if this is skewed or symmetric. So I'll select the data, insert a pivot table. Let's put it right there. I want to count up the values, not add them up. And let's group into classes. Sure, we'll just use the default that Excel wants to go with. And then I will insert my bar chart. And I would say that this is fairly symmetric. It's not perfectly symmetric, but in the real world you're very rarely going to encounter anything that's perfectly symmetric. And I would say that this is, roughly speaking, kind of a bell shape, kind of a symmetric distribution. Okay, so the shape would be bell-shaped. Let's write that down. So as far as the shape is concerned, this is numerical data, and it's bell-shaped. In other words, it's a symmetric distribution, right? It's symmetric. And since it's symmetric, that means that for the center, the measure of center we're going to report is the mean. Okay, symbol for the mean is x bar. And the measure of spread we're going to report would be the standard deviation. The symbol we use for the standard deviation is S. We'll use Excel to get those values. And then as far as outliers are concerned, we'll make a box plot to see if there are any outliers. Let's head over to Excel and fiddle around a little bit. Okay, so for the mean, I'm going to say equals average and select the data. For the standard deviation, I'm going to say equals standard dev.s. Okay, select the data. Ooh, I got an extra value in there. Let me edit that. Okay. There's the standard deviation. And then as far as outliers are concerned, I'll just select that and insert a box plot. And yeah, it doesn't look like there are any outliers. In fact, this is almost like perfectly symmetric, it looks like. Okay, no outliers. Let's write it down. So the mean x bar, let's round to one decimal place. So we'll say x bar is approximately 50.5, and S, our standard deviation, is approximately 21.0 if I round to one decimal place. No outliers. Okay, the box plot didn't reveal any of those. So there you go. That's what a data profile looks like, basically. Okay. Now, in addition to that, we talked about how to make sense of frequency tables and graphs and things like that in this unit. So let's practice and kind of review some of that stuff. Number 2 here says, identify each of the following data sets as categorical or numerical. If numerical, decide whether they are symmetric or skewed. And then it says, determine but do not calculate, the best measure of central tendency and dispersion for the data set. Measure of central tendency is another way to say measure of center, and measure of dispersion is another way to say measure of spread. So, looking at this first data set, It says a group of students recorded the colors of cars in a parking lot. Their results are shown below. What you'll notice is we don't have the raw data here. If they're recording the colors of cars in a parking lot, then the raw data would have looked like a list of car colors, right? It would have looked like white, silver, white, red, blue, white, silver, green, black, gray, gray, white, right? It would have been this long list of car colors. Somebody has already done some work and summarized this into a frequency table for us. And the reason I'm pointing this out is because oftentimes students get confused because they see these numbers and they say, oh, well, it's numerical. Look, it has numbers. But you have to think about what the raw data would have looked like, okay? The raw data would have been a list of car colors. It would have been categorical, not numerical. So this is a categorical data set. Since it's categorical, the best measure of central tendency and dispersion, so best measure of center, would be the mode, which in this case is not that hard to calculate. It's silver, right? Silver is the thing that occurred most frequently. We weren't asked to calculate the mode, but in this case it's so easy to do. That would be our best measure of center. And then best measure of dispersion. Well, I should maybe be a little more careful about this, because it's not that the IQV is the best measure of dispersion, but it is the only measure of dispersion that we've talked about in this class for qualitative or categorical data. So, so that's the one that we would have to use. This would take a little bit more work to calculate. Fortunately, we weren't asked to calculate it. Oh, and by the way, originally I was going to ask, does the dataset have any outliers? But I think on your notes you won't even have that question, because I've decided to remove it in the interest of time. This is already going to be a super long lecture, so we won't talk about whether or not these datasets have outliers. We've kind of discussed that already, and we'll discuss it a little bit more in the future. But that's part A. Looking at part B, it says a disc golf club recorded the age in years of its members, and the results are summarized below. Remember, our task on this example is to determine if the data that we're given are numerical or categorical. And in this case, we would say these ones are numerical, because if you think about what the raw data would look like, it would be a list of ages, right? It would be a list of numbers. So this is numerical data. And since it's numerical, the best measure of center, okay, I got ahead of myself. Hold on a second. The best measure of center could be the mean, or it could be the median, depending on whether this data set is symmetric or skewed. So I think the best thing to do probably would be to make a histogram out of this. I don't even know if I have this data in Excel though. If not, oh, I do. Okay, I do. Okay, so let's insert a histogram for this data set. This looks to me to be skewed left. Right? I would argue that this is a skewed left distribution. So the best measure of center would be the median. Okay. So this is numerical, and it's skewed left. So the center, best measure of center would be the median. We could try to estimate the median, but we weren't asked to, so I'm just going to leave it at that. And the best measure of spread would be the IQR. Again, because it's a skewed data set. Let's look at some more examples. Let's say instead of a frequency distribution, the summary that you were given was a graph. In this case, it looks like we have a histogram. So which means that this data set must be numerical. We know at least that much, right? We're asked to identify the following variables as categorical or numerical. This is numerical. We know that because it's a histogram. But also, if you look at the x-axis, right, the categories are numbers here. This histogram is supposed to represent the weights of 15 newborn babies. Weights are numerical. So, okay, so this is a numerical. In fact, more specifically, they're continuous, right? But we don't need to go that far. We just need to decide if they're numerical, and then whether the data are symmetric or skewed. I would call this a symmetric distribution. It looks pretty symmetric to me. It's not perfectly symmetric, but it's more symmetric than skewed. So I would say that this is numerical and symmetric. This time it asks us to calculate or approximate the best measure of central tendency. They're not asking for a measure of spread. The best measure of spread here, since it's symmetric, would be the standard deviation. But we weren't asked for that information. We just want to give the best measure of central tendency. Okay, which in this case would be the mean. Since it's a symmetric data set, we would use the mean. So best measure of center would be the mean. Okay, so let's estimate it. In order to give a good estimate, we don't have the raw data, so we can't just calculate the mean in Excel like we normally would. Instead, we'll just have to kind of give an estimate for each, for what the data set would have looked like that this came from. So for example, we've done this before, but just to give an example, there was one individual, one newborn baby that weighed between 2 and 2.5 kilograms. So the dead center of that class is 2.25. And since I don't know exactly what the baby weighed, that's going to be the best estimate for the weight of that one baby. Okay, so if I'm trying to kind of reconstruct my data set, my first value would be 2.25. And keep in mind, of course, this is just an estimate. There were 3 babies that weighed between 2.5 and 3 kilograms. The dead center of that class is 2.75. And I'm going to write down 3 of those, right, since there were 3 of these. And we would do the same thing for the remaining classes. So the dead center of this class is 3.25, and there were 5 babies in that category. And of course, if you don't want to write down all of these values, that's totally fine, because you could just use multiplication. You could say, well, it's 3.25 times 5, right? And here we'd have 3.75 times 4. But I'm just going to go ahead and write them down since that's how I started to show my work. I might as well finish it this way. And then finally, there were 2 babies between 4 and 4.5 kilograms. The dead center of that would be 4.25. So I have a couple babies that are something like 4.25 kilograms. Again, these are just estimates. We don't know exactly what the raw data set would have looked like, but this will be a good estimate for it. And so then to give an estimate for the mean, well, we could just say that it's going to be the sum of these numbers divided by the number of these numbers, which I think is 15, right? So we would say it's 2.25 plus, let's see, 3 times 2.75 plus 1, 2, 3, 4, 5 times 3.25 plus 1, 2, 3, 4 times 3.75 plus 2 times 4.25. Okay, and then we would divide that by 15. Let's head over to Desmos to see how much that is. So give myself a little fraction bar. I've got 2.25 plus 3 times 2.75 plus 5 times 3.25 plus 4 times 3.75 plus 2 times 4.25, and then we'll divide that by 15. So I'm coming up with 3.35. So that's 3.35. That would be a pretty good estimate for our measure of center. Okay, we could do the same thing for the measure of spread, right? We could enter these values into Excel and then calculate the standard deviation, right, to give an estimate for the best measure of spread of this data set. But we weren't asked to do that, so I'll leave it there, right? This is all we were asked for. Okay, part B says a group of students was asked what their dream job was. Their responses are summarized below. Again, our task here is to decide if this data is, or if this distribution is, if the variable here is categorical or numerical. And so again, think about what the raw data would have looked like. Students were asked what their dream job was. They're not going to answer 17 or 42.6. They're going to answer, oh, my dream job is to be an athlete or a president of the United States, right? Well, those are categorical data. So this must be categorical. Since it's categorical, it doesn't really make sense to talk about whether it's skewed or symmetric, because we could rearrange these bars in any order we want, right? So the shape doesn't really make sense to talk about, but we would say it's categorical data for sure. Since it's categorical, the best measure of center would be the mode. The mode. Now, a lot of times on a problem like this, students might be tempted to say that the mode is 13 because there were two categories that repeated 13 times. But that's wrong on two counts. Number one, it's wrong because you're confusing the counts with the categories, right? The answer here, since this is a qualitative data set, since it's a categorical data set, the answer should be a category, not a number, okay? And for another thing, just because there were two bars that both repeated the same number of times doesn't mean that that's the mode. The mode is the bar that repeats the most, right? It's the bar with the greatest frequency, which is neither of these two categories. It's this category, right? This category was the one with the greatest frequency. So the mode should be not 40, but athlete. Okay, that would be our measure of center. So this is a categorical data set, and the mode is athlete. By the way, if we wanted to know what the modal proportion was, in other words, what proportion of students said that athlete was their dream job, well, then we would take our 40 athletes and divide that by the total number of people in the study, which I'm not going to take the time to do, but it would be whatever our sample size was here, right? But we can practice that on a future question. That's how that one would work. Okay. Two more examples of this, and then we'll talk about, we'll review comparing data sets. But let's just run through two more examples real quick. Let's practice interpreting what a boxplot is telling us, the information a boxplot is telling us. Now, unfortunately, this did not print so well, so let me just try to emphasize where the median line is in this boxplot and where the mean is in this boxplot. Hopefully on your printout it's a little bit more clear, but you should be able to the lighting is kind of weird on my camera right now, but you should be able to see those on your page, hopefully. Anyway, it says the graph below represents the number of orders for mango sticky rice ordered from a Thai restaurant on different days over the course of 70 days. Is this categorical or numerical? Well, you wouldn't be able to make a box plot out of categorical data, so you know that this is numerical. But you also know that it's numerical if you think about what the raw data looks like, right? This is supposed to be the number of mango sticky rice orders. Okay, if you were asked how many orders for mango sticky rice did you get today, you're not going to get. They're not going to say blue, right? They're not going to say dog. They're going to say 14, right? They're going to say whatever number it was, right? They're going to say we had 40 orders for mango sticky rice today. So this is numerical data. So it's definitely numerical. We're asked to describe the shape of the distribution. Normally, to describe the shape, what we would do is look at a histogram. But in order to make a histogram, we have to have the raw data, which we aren't given here. We just have this box plot to go off of. Fortunately, we can kind of make sense of the shape of the distribution by looking at the box plot. Notice that, well, let me just tip this on its side to make this a little bit easier maybe to see. But notice that if I tip it on its side, the left, again, the median line is right here. The left-hand side of this box is wider than the right-hand side of the box. And the left whisker is longer than the right whisker. And there are also a few outliers over here on the left and no outliers up here on the right. So overall, I think that this whole, it looks like you took a symmetric box plot and then stretched out the left-hand side, which means this is a skewed left distribution. So this is numerical and it's skewed left. Okay. Part B says to estimate the mean and the median. Well, okay. So I don't know why the lighting is better 2 inches to the right, but for some reason it is. Okay, so the mean is given by this x, which to me looks like it's maybe right at 55 or maybe a little bit below that. Maybe it's like 54 or something. So the mean, x bar, is about 54. Okay, and the median, m, the median is given by the line inside of your box, and that line looks like it's maybe at, well, let's see, halfway between 55 and 65 would be 60, and this is just a little bit below that, so maybe this is like 58 or something. Approximately 58. This box plot doesn't have any data labels, so it's hard for us to tell exactly, but those would be my guesses for those estimates. If you have the data labels, it would be even easier, right? Part C asks us to estimate the IQR. Oh, wait. We were asked which of these measures of center is a better measure of center. Well, this is a skewed left distribution, so we would use the median, right? The median is better. In this case, because the distribution is skewed. Okay, now on to part C. It says estimate the IQR. Well, remember that IQR is Q3 minus Q1. Okay, so looking at our box plot, the way that we see Q1 and Q3 is there are these values right here, right? This one would be Q3, and this one would be Q1. They're the edges of our box. Q3, to me, looks like it's just below 64, or 65, so maybe it's like 64. And Q1 looks like it's almost dead center, so dead center between 45 and 55, so I'll call it 50. So Q3 I'm going to say is maybe 64, and Q1 I'm going to say is 50. So to calculate the IQR, I would say this is approximately 64 minus 50. By the way, I don't know if you can hear the students in the hallway. I apologize if they're disturbing you. They're having a good time doing something. Anyway, 64 minus 50 would be 14. So there's an estimate for the IQR. And then finally, part D says, are there any outliers in this distribution? Yes, clearly, right? These three are outliers. Yes, there are 3 outliers. And we might want to identify them. They are approximately let's say something below 20, maybe like 18. This one is just below 25. Maybe this is like 22 and 23. That would be my best guess for those 3 outliers. But I don't know why I boxed that, because the real answer to the question is simply yes. Are there outliers? Yes, there are. Right, there are 3 of them. Okay. And then we've got one more bar chart. Let's practice interpreting this bar chart a little bit. It says a randomly selected group of 90 students was asked what their favorite day of the week was. And here we have that bar chart. Okay. Is this categorical or numerical? Well, let's think. What would the raw data look like? Somebody asks you, what's your favorite day of the week? You don't say the square root of 7, right? You say Friday or Sunday or whatever your favorite day of the week is. So clearly you're going to be giving categories as your answers. So we'll say categorical. Since it's categorical, we don't have to talk about whether it's symmetric or skewed. That doesn't really make sense. So part B asks us to calculate the mode and the modal proportion. This is very similar to the dream job scenario, right? But remember, the mode is the category that repeats most often, which in this case looks like it's this category right here. So the mode is not 27, the mode is Saturday. Okay. The modal proportion, so the proportion for Saturday, P hat sub sat for Saturday, this would be 27 out of the sample size, which was 90. We were told that there were 90 students in this survey. So it would be 27 out of 90. Let's calculate that real quick. 27 out of 90. Oh, is exactly 0. Oh, I should have been able to do that in my head. Come on. Am I a math teacher or what? Okay, so there's the mode. And there's the modal proportion. 0.3. So 30% of participants said that Saturday was their favorite day of the week. Okay. Part C, I was going to ask you to compute the IQV, but we've practiced that already in this section, so we'll skip that. But Part D asks us to calculate the sample proportions of any outliers in the data set. Well, again, it's kind of hard to say when you're looking at a categorical data set. There isn't like a set in stone criterion for determining when you have outliers. But what I would point out is that it's very unusual for anybody to say that Monday is their favorite day of the week. Not just because Monday is a bad day, but because in the data set only one person said Monday, right? So that's kind of an unusual thing that I think is worth pointing out. So we'll say only one person likes Mondays. So that's a little unusual. The sample proportion of people who said Monday is 1 out of 90. And 1 out of 90 is approximately 0.011. So only about 1.1% of participants said that they like Mondays, right? Which is pretty unusual. Like pretty much anything less than 5% is usually considered to be fairly unusual. You can see that's not going to be the case on Tuesdays or Wednesdays or Thursdays. Those percentages will all be more than 5%. So I think that'll do it as far as identification of outliers here. So that's the moral of the story for data profiles, right? Trying to describe a data set. Another of our main topics in this unit, we had 3, right? So this is the second of our 3 main topics, is comparing data sets. Again, there's not a lot of new information to share here. We're just going to practice comparing data sets. Let me just say before we do, I think it goes without saying that it only makes sense to compare data sets if you have some reason to make the comparison. And in particular, it would really only make sense to compare data sets if you're trying to compare the same variable. Okay, for example, comparing the weight of elephants to the weight of giraffes is a useful comparison, right? If you want to know which animal is heavier, right, you're comparing the same variable, weight to weight. So you're comparing the weights of 2 different groups. That's a useful comparison. Comparing children's favorite fruit to adults' favorite fruit is also a useful comparison, right? You're comparing the same variable, favorite fruit. You have 2 different groups, children and adults. That makes sense. But comparing the weight of elephants to children's favorite fruit is not a useful comparison, okay? So we'll take it for granted that when we're asked to compare data sets, it makes sense to do so, which means that we're going to be comparing the same variables in the 2 different groups that we're trying to compare. Let's review how to do this. If you have data sets and the variables are numerical, remember you have to be comparing the same variables, so they would both have to be numerical. Then what you're going to do, first of all, is create a side-by-side box plot. That's going to be the best visual comparison that you can get, I think, is just a side-by-side box plot. That'll lay out both of the data sets on the same graph, and you can see really clearly like which one has a larger weight or whatever, which one has a larger mean, which one has a larger median, which one has more spread, etc. So side-by-side box plot's really great for a visual comparison. As for numerical comparisons, the numbers that you should compare depend on the shape of the distributions in question. If both of your data sets are symmetric, then you should compare the means and the coefficients of variation for the data sets. If at least one of the data sets is skewed, though, you should compare medians and quartile coefficients of variation, QCVs. Okay? So that's what we do when we're comparing 2 numerical data sets. If we're going to compare 2 categorical data sets, then the best thing to do would be to make a side-by-side bar graph to get a visual comparison, right? And then the statistics to compare would be modes and indices of qualitative variation, right? So modes and IQVs. If one of the data sets is numerical and the other is categorical, then there's no way that that's a useful comparison to make. We'll talk later on in the semester about trying to decide if one variable affects another variable, and in that case it would be worthwhile to compare numerical and categorical variables to see if this categorical variable has some effect on this numerical variable. That's totally valid. But if all we're trying to do in this section right now is to just compare 2 distributions, 2 data sets, and so it really doesn't make sense to compare a numerical data set to a categorical one. So we won't worry about that situation. Anyway, here's a summary of what we're saying. Again, this is a pretty good summary. Depending on your data, your type of data, if you have a numerical data set that's symmetric, or sorry, 2 numerical data sets that are symmetric, that are both symmetric, then you'll compare their means and their CVs. If you have two numerical data sets and at least one of them is skewed, then you'll compare their medians and their QCVs. And then if you have two categorical data sets, you'll compare their modes and their IQVs. Let's walk through some examples. Number 6 here says, a survey of nearly 200 colleges and universities was taken. The admission rates of the schools was recorded. And I'm not giving the data here because there were 200 and I wasn't about to write them all down in this space. But they're recorded there in the spreadsheet, so we'll take a look at them. We're asked to compare the distributions of public and private school admission rates. Okay, so let's do that. So this is example 6. We have the admission rates of a bunch of private schools over here, and then a bunch of public schools over there. There were more private schools in this study than public schools, it looks like, and that's totally fine. These data sets are numerical, okay? So we're going to either compare means or medians for the measure of center, and then we're going to either compare the CVs or the QCVs for the measure of spread. To decide which is which, or to decide which one to go to, we should look at some histograms of these two variables so we can decide if they are symmetric or skewed. So I'm going to insert a pivot table for private schools, put together a little distribution for them. Let's change this so that I'm counting up the number of people in each category, and let's go ahead and group these. And I'll just use the default groups that Excel wants to give me. And histogram. Insert. Bar chart. Ooh, that's beautiful. That's like almost perfectly symmetric. Okay, let's do the same thing for public schools. Insert pivot table. Let's do this right next to the other one. Let's change sum to count, and we'll group. And again, I'll just use the default that Excel wants to give me, and I'll insert a histogram there. Okay, so another symmetric one. This one's not quite as beautiful as the other one, but it's symmetric. It's definitely symmetric. It's not perfectly bell-shaped, but it's a symmetric distribution. So, okay, so it looks like we've got two symmetric distributions here, and therefore the best measures of center to compare would be means, and the best measures of dispersion to compare would be CVs. So I'm going to make a little table down here. We want the mean. In order to compute the coefficient of variation, we'll need to get the standard deviation, and then we can get the CV. And I'm going to do this for private schools, and I'm going to do it for public schools. So let's compute these things. For the mean of private schools, I'm going to say equals average, and then select the private schools. For the mean of public schools, I'm going to say equals average, and select the public schools. Okay, so just comparing the averages, you can see that public schools have a higher acceptance rate than private schools do. What did I say? Public schools have a higher acceptance rate than private schools, which is not surprising. Okay? Let's compute standard deviations. So standard deviation dot S for sample. Okay. There it is for private schools. There it is for public schools. And then we'll want to compare CVs. Rather than comparing standard deviations, we'll compare coefficients of variation, just because the means are not the same, and so you know, you can't necessarily say that there's more spread amongst private schools than there is amongst public schools just by looking at the standard deviations, although that may be the case. We'll see. But to get the CV, we're going to say equals, and I want to take the standard deviation and divide it by the mean. And I'm going to do this for both groups. Equals standard deviation divided by mean. Okay, so private schools do in fact have more spread. There's more variability in the admission rates of private schools. That's pretty much it, although one thing that I mentioned that we haven't done yet is it's good to get like a side-by-side box plot. So let me select these two things. I wonder if, let me just select those two columns and I'll say insert, and let's insert a box plot. And this box plot I think is a good summary that kind of verifies some of the things that we've discovered, right? Ooh, let me give myself a legend here so that I can see which box corresponds to which type of school. So the blue box plot is for private schools and the orange box plot is for public schools. And again, these are acceptance rates. This is what percentage of students who apply to the school are admitted to the school, right? Get into the school. And you can see really clearly that public schools have a higher admission rate than private schools do, okay, on average. And you can also see really clearly that there's more variation in the acceptance rates of private schools, right? Some private schools are very selective. If we add some data labels, yeah, some private schools have an acceptance rate as low as 15%, right? Or probably even lower. Anyway, so looking at a side-by-side box plot is really, really helpful when you're wanting to compare data sets. But let's write these things down. Ooh, hold on. I want my legend back. I don't want the data labels though, because they're kind of cluttering up the picture. I also kind of want to get rid of this one and just delete it. Okay. But let's go back and write some things down. So the mean, I'm just going to write on my page a little bit, and then I'll show you what I'm writing. So let me just make a note of this real quick. I'll say both data sets are numerical and symmetric. And therefore, the best measure of center to compare is the mean. I'm just going to make that same table that I made in Excel, right? Mean and CV. I don't need to report the standard deviation. I just need to report the coefficient of variation. But I'm going to do this for private schools and for public schools. Okay. So the mean for private schools, let's round to, we'll just go to one decimal place. So for the private schools it was 58.8. For public schools it was 69.3. And the CVs would be about let's go 2 decimal places here, 0.32 versus 0.25. Okay. And that's it. That's a good comparison. We might want to say a few words in summary. We could say something like private schools are more selective, right? They have lower admission rates than public schools. Private schools also have more variety in their admission rates. Okay, and that's a good comparison. Moving on to the next one. Number 7 says, last semester, a professor tracked the seating habits of nearly 100 students and recorded their final grade. Compare the distributions of grades for students who sit in the front versus students who sit in the back. Okay, that's example 7. Students who sit in the front versus students who sit in the back. Right off the bat, I noticed that this is categorical data. Okay, so it doesn't make too much sense to talk about the shape of the distribution. But it's categorical data, so what we'll want to do is compare the modes, and we'll want to compare the IQVs, right? The indices of qualitative variation for both of these data sets. In order to compute the IQVs, I need to have a relative frequency distribution for each data set, so that would probably be the place to start. And I kind of want to get a relative frequency distribution for both of these anyway, so that I can get a sense for what the distribution is, what the breakdown is. I can also use it to get a side-by-side bar graph. So let's play around a little. I'm going to try to make this all into one pivot table, and I think in order to do that, you can't have a blank column between your two columns. So let me just delete this column. And now I can select all of this stuff. I just hit Control A, right? Now it'll select all of your data. And then I'm going to go to Insert, Pivot Table. I'll do that right here in our existing worksheet. Okay, so I want to count up how many people sit, or the grades for people that sit in the front, and I want to count up the grades for people who sit in the back. Okay, so by dragging front to the rows tile, that'll give me the grade categories, and then I can drag front and back both to the values tile, and that'll give me the appropriate columns. I'm going to rearrange some of these because B plus, I notice, should come before B. It should be between A minus and B. So I'm going to select that cell and then go over to the edge of the cell, and then I can drag it up right there. Same thing with C plus. Let's move that between a B minus and a C. Okay, I think those are in the correct order now. This is ordinal data, by the way, so I've got it in the correct order. If I wanted a side-by-side bar graph out of this, I can select this and say Insert and bar graph. And then it gives me a nice side-by-side bar graph. Oh, you know, of course, I don't actually want a side-by-side bar graph of the counts or of the frequencies. I want a side-by-side bar graph of the relative frequencies because there weren't the same number of students in these two categories. So let me change these. Let me change these to percent of column total. Okay, so that's even better. The graph didn't change a ton, but now I have these percentages to work with, which is really nice. Okay, but now let's talk about the measure of center to compare, right? The best measure of center to compare, since these are qualitative variables, would be the mode. So for students who sit in the front, it looks like there's a tie between an A minus and a B plus. And for students who sit in the back, it looks like the mode is B plus. Okay. So that's worth noting. We'll also want the IQVs, but let's write down what we've discovered so far. Okay, so both data sets are categorical. Consequently, we're going to compare modes and IQVs. So I'm going to do this for students who sit in the front and students who sit in the back. The modal grade for students who sit in the front of the class, I think we said was an A minus. There was a tie between A minus and B plus. And then for the people who sit in the back, it was just the B plus. That was the mode. So 2 modes for the front and just 1 mode for the back, right? It was B plus. By the way, I can't believe how good this class is. Look at these grades. Nobody failed. That's kind of incredible. Okay, let's compute the IQV now. This is a little bit more of a pain, but we can do it. So I'm going to select my pivot table, copy it, and then let me paste it down here, but I'm just going to paste the values only. Okay. And now here I want to compute the squares of those proportions. So I'm going to say equals, this will be actually, let me erase that. So let's do the front and the back. Okay, so the squared proportions here, I'm going to say equals this proportion squared. And hopefully it will let me just autofill all of this stuff. Shoot. I was just doing this and it let me autofill, and I don't know why it's not letting me autofill now. What a pain. Equals this squared equals this squared equals this squared equals this squared and equals this squared. Okay, and then I want to find the sum of those, so I'm going to say equals sum, and we'll add these up. Okay, and then we'll do the same thing for the back. So equals this number squared equals this squared equals this squared equals this squared equals this squared, this squared, and this squared. Okay, and then we'll sum those up. Okay, so now to get my IQVs, let me copy this number. How many categories do we have? 1, 2, 3, 4, 5, 6, 7. So K equals 7 in this case. I'm going to copy this number, copy, and then I'm going to go over to Desmos. So remember, K equals 7. The formula for the IQV is K times 1 minus that number that we just computed divided by K minus 1. So there's the IQV for people who sit in the front of the class. And then for people who sit in the back of the class, let me copy that number. And we'll say, again, K times 1 minus that number we just computed in Excel divided by K minus 1. Okay, and there's the IQV for people who sit in the back of the class. There's not a huge difference, okay? Oh, I gotta write those numbers down. Let's round to 3 decimal places. I'll say for the front, the IQV is approximately 0.934, and for the back, it's approximately 0.923. Okay. And that's that. Um, in comparing these two data sets, the modes are not that different. If you're looking at the overall grade in the class, it's like, okay, people who sit in the front, you know, there were a few more of them who got an A minus than a B plus, but there's just not much of a difference between an A minus and a B plus anyway, right? There's also not that much of a difference in their spreads, you know. There's a little bit more variety among people who sit in the front of the class, but it's not that much different. There's not that much of a difference in the variety of these two groups. If we look at the side-by-side bar chart that we came up with, you can see that, yeah, there's just not that much difference in your overall grade if you sit in the front of the class versus if you sit in the back of the class. Now, I'm not saying that this is true generally speaking, but for this particular data set, that's the case, right? There's just not much of a difference between students who sit in the front versus students who sit in the back. You could maybe argue, well, people who sit in the back were more likely to get a B plus, but less likely to get an A minus, slightly, right? Or rather, they're actually more likely to get an A minus, aren't they? But they're less likely to get an A, a full-blown A, but only slightly so. People who sit in the back are more likely to get a B minus, and they're more likely to get a C plus, but less likely to get a B. So, you know, maybe you could kind of argue that it's good to sit in the front of the class, but there's just not, I don't think there's really good evidence to say that. I think that in this case, these distributions are pretty much the same. Anyway, that may be worth writing down. We can say these distributions are very similar. It does not seem to be the case that your grade is affected by where you sit. Okay, and again, I'm not saying that that's the case in general, but for this particular data set, that seems to be what's going on. Okay, let me give you one more. Again, I know that this is a long lecture, but hang in there. I'll give you one more example where we're comparing two data sets, and then we'll move on to our third major topic. So let's get to it. Number 8 here says 50 women and 50 men were asked at what age they thought they would retire. Compare the distributions of projected retirement age for women and men. Okay, let's take a look at the data set. So here I've got numerical data for sure. I'm going to need to make some histograms so that I can decide if these data sets are skewed or symmetric. So I'll start off by making a pivot table for women. Let's group into classes. Oh, we almost don't need to. Oh, hold on a second. First I need to change this so that it's, instead of adding these up, it's just counting the number of women in each class. Okay, but yeah, I almost don't even need to group into classes, but we'll group anyway. We'll use Excel's, I don't like that actually. Let's group by 5 maybe, instead of by 10. Okay, that's a little bit better. Okay, and then we'll do the same thing for the men. Insert a pivot table. Let's do men over here. Let's count the values rather than adding them. And let's group. Okay, this time grouping by 10 gave us a good number of classes, so I'm happy with that. Histograms now. We'll insert some bar charts. And you'll notice that I've been lazy. I haven't really been making these wider, even though we really should. But okay, so there's our histogram for women. And for men, get rid of that. Okay. The men seem pretty symmetric to me. The women seem skewed left, though. And since one of our data sets is skewed, we're going to have to compare medians and QCVs, okay? Medians and quartile coefficients of variation. Let's write down what we've discovered so far, and then we'll come back to StatCrunch and we'll compute those values. So both data sets are numerical. The women are skewed, and the men are symmetric. Okay, consequently, the best measures of center and spread to compare are going to be the median and the QCV, okay, for each group. So we'll do this for women, and we'll do this for men. Okay, let's just remind ourselves that the QCV is the IQR, in other words Q3 minus Q1, divided by Q3 plus Q1. So to get the QCV, we'll just have to compute the quartiles, Q3 and Q1, and then we can compute the QCV from there. The median is easy to get. So let's head over to Excel. So for the median, I'm going to say equals median. Click on the women. Okay. For the quartiles, Q3, I'll say equals quartile.inc. Select the women and say comma 3 so that I'm getting the third quartile. For the first quartile, I say equals quartiles.inc. Select the women, comma 1 to get the first quartile. And then let's do the same thing for the men real quick. Equals median. Select the men. Okay. Q3. We'll say equals quartile.inc. Select the men, comma 3 for the third quartile. Say equals quartile.inc. Again, select the men, comma 1 for the first quartile. Okay, and so then to get QCVs, so let's come back over to the women. QCV. You could do this in Desmos. I'm just going to do it here in Excel. Okay, so I'm going to say that this equals. I'm going to open up some parentheses and say Q3 minus Q1. Close the parentheses, and then divide that by. Open up another set of parentheses and say Q3 plus Q1. Now, if you're not comfortable doing that, that's fine. Just use Desmos. But this is a little bit quicker for me. QCV equals Q3 minus Q1 divided by Q3 plus Q1. Okay, so it looks like the men have a little bit more spread. Okay. Looks like the median age for retirement is about the same for each group. That's kind of interesting. Another thing we would want to look at would be a side-by-side box plot. So let's insert one of those. Oh, and let's see. All right. So it looks like, yeah, I mean the box plot is kind of indicating exactly what we're seeing. The median is the same for both groups, but the men have a little bit more variety in their data set. So that's kind of interesting. Okay, let's write these things down. The median for women was 65, and for men it was also 65. That makes sense. That's the typical retirement age. The QCV for women was, let's round to 3 decimal places. We'll say 0.077. And for men, it was, exactly equal to 0.12. Okay, and just to give like a little summary of that, I would say men and women generally plan to retire at age 65. However, men are less consistent. Or in other words, they have more variety. Men are less consistent about when they will retire. Their answers vary more than women's answers. Okay, so that's that. That's how we compare data sets. Now, we've been going for almost an hour and a half at this point, but I promise this next topic won't take nearly as long to review. The last main topic in this chapter, in this unit, was comparing the relative position of individuals. And there were 2 main tools that we used to do this. One of them was the percentile, or really the percent rank. The other one was the z-score. And those 2 concepts were tied together by the empirical rule. The empirical rule tells us that 68% of values fall within 1 standard deviation. If a value is 1 standard deviation above the mean, then z equals 1. If it's 1 standard deviation below the mean, then z equals -1. So basically, the empirical rule is saying that 68% of the values are going to be between z equals -1 and z equals +1, right? 95% of the values are going to be between z equals -2 and z equals +2, and so forth. So the empirical rule ties those concepts together. Let's just practice. Okay, I think I've got three examples in total here. So number 9 says, the data below represent the IQ scores of 50 randomly selected students. In part A, we're asked to calculate and interpret the percentile rank of the student with an IQ of 109. Okay, so remember, we'll use the equals percent rank .inc. We'll select the data, and then we'll put in the value of 109, and this will tell us at what percentile 109 falls under. Okay, let's see what we get. This is for example 9, so we'll say equals %rank.inc, select the data, and say we want the percentile rank for an IQ score of 109. So that would be 0.836. Or in other words, 83.6%. So if you have an IQ of 109, then that means that your IQ score is better, it's higher than 83.6% of people. So that's kind of interesting. That's the interpretation. We would say an IQ of 109 is a higher IQ than 83.6% of people. So that's part A. Part B asks us to calculate the sample mean and standard deviation of the data, and then calculate and interpret the z-score for a student with an IQ of 109. Well, okay, so for the sample mean, x bar, we'll say, we'll use the average function. We've been doing this all throughout this section, but we haven't been really showing our work, so let me just at least show our work on this last part. So we'll use the average function. Equals average of the IQ scores. And for the standard deviation, we'll do the same thing. Well, not the same thing, but a similar thing. We'll say equals standard deviation dot s for sample, and compute the standard deviation there. So for the mean, it's about 99.2, and for the standard deviation, it's about 9.7. To show my work, this was and I think we said it was about 9.7. Yes, 9.7. Okay, and then we want to calculate the z-score for a student with an IQ of 109. Well, the z-score, the formula for the z-score, is our observation x minus our mean x bar divided by our standard deviation s. So in this case, that's 109 minus 99.2 divided by 9.7. Let's see. We'll go over to Desmos this time. 109 minus 99.2 divided by 9.7. That's about 1.01. So there's our z-score. So this individual who has an IQ of 109 is almost exactly one standard deviation above the average IQ score. That's what the z-score means. So we would say, for our interpretation, an individual with an IQ of 109 is almost exactly one standard deviation above the mean IQ score. Okay, part B or part C asks, how do the percentile rank in part A and the z-score in part B relate to each other? which is kind of a vague question, but the reason I put it in here is because I wanted to emphasize how the empirical rule ties percentiles and z-scores together. So you may remember, let me just draw a quick picture here. Okay, you may remember that the empirical rule says that 68% of the data are going to fall within one standard deviation of the mean. Right, so here's one standard deviation above, right, z equals 1. And here's one standard deviation below, z equals -1. And 68% of the values are in here. To be more specific, we could say, well, 34% of the values are going to be here, and 34% of the values are going to be there. We can also say, because this is a symmetric distribution, that 50% of the values fall below the mean, right? 50% of the values are below the mean. And that means that in total, we would expect from the empirical rule that about 84%, right? 50% plus this 34%. So about 84% of the values are going to fall below a z-score of 1. Right? So I would say this, the empirical rule predicts that, let me just show my work a little, 50% plus 34% equals 84% of IQ scores will be less than 1 standard deviation below the mean. Or, sorry, they'll be less than 1 standard deviation above the mean. Above the mean. That's exactly verified by looking at the percentile rank of an IQ score of 109, because 83.6% rounded to 1 decimal place is 84%, right? So we could say we have verified that 109 is, or maybe I'll say that a score of 109 is 1 standard deviation below the mean, and a score of 109 is at the 84th percentile. As predicted. Okay, so I just think that's kind of a beautiful example, right? To show that, yeah, the empirical rule does a good job of kind of tying those concepts together. I'm not going to ask you to think through something this complicated on a test, right? Like on a test, you forget half of what you know anyway, so you won't be asked to do something this complicated on a test, but I thought it was worthwhile to at least one time kind of go through that thought process. Okay, let me give you a couple more just quick examples here. This next one, number 10, says 10 students were given a test. Half of them, group A, took a practice test before taking the real test, and the other half, group B, did not. Their results are listed below. Use percentile ranks to determine who did relatively better, a student from group A who scored a 71, or a student from group B who scored a 68. Obviously, the score of 68 is worse, okay? But the question is the score of 68 worse relative to the fact that group B didn't have a practice test? So to answer that question, we'll use percentile ranks. So this data should be in Excel. Yeah, example 10. Okay, good. So for group A, let's do equals percent rank.inc for group A, and the person from group A had a score of 71. Okay, so that's group A. And then for group B, we'll say equals percent rank.inc, select the group B group, and the person from group B scored a 68. So the group B person scored relatively better, right? Their score is better relatively speaking, because they have a higher percentile. They're at a higher percentile among their peers. Okay, so let's show our work and write down our answers. But for group A, we said equals percent rank .inc. We selected the data, and then we entered a score of 71. For group B, we said equals percent rank .inc. We selected the data, and we entered a score of 68. And for group A, this came out to 0.413, and for group B, this came out to 0.551. So in other words, the group A student, right, this student who scored a 71 is at the 41st percentile among group A students, and this student who scored a 68 is in the 55th percentile among group B students. So they did better, relatively speaking. The student from group B did relatively better. Again, in absolute terms, they did worse, right? 68 is worse than 71. But relatively, they did better, right? 0.551 is bigger than 0.413. Okay. This would be an interesting data set to compare, right? You might want to know which group had a better average test score. That might convince you that taking practice tests is a good idea. But I'll leave that for you. One last example. The purpose of this example is just to point out that you really try not to get confused about when you're being asked to compare two data sets as a whole versus when you're being asked to compare two individuals in those data sets. Okay, so here's an example of what I'm talking about. Number 11 here says men have heights with a mean of 69.1 inches and a standard deviation of 2.8 inches. Women have heights with a mean of 63.6 inches and a standard deviation of 2.5 inches. Part A says, relative to their average heights, which group has more height variety, men or women? That might seem like kind of a confusing question, but remember the way that we measure the amount of variation in a data set is with a measure of dispersion. In this case, we were given the standard deviations, so that's what we'll use, okay, as our measures of dispersion. But we don't want to just compare the measures of dispersion. If we do that, then clearly men have more variety than women because 2.8 is more than 2.5. But we need to look at that relative to their average heights, right? So we'll divide those standard deviations by their corresponding means. So when we do that, by the way, that's called the coefficient of variation, right? So we want to compare CVs, not just standard deviations. So for men, the CV, well, generally speaking, it's standard deviation divided by mean. So for men, that's going to be 2.8 divided by 69.1. And similarly for women, right? standard deviation divided by mean. So for women, that's going to be 2.5 divided by 63.6. Let's head over to Desmos and see how much these are. So 2.8 divided by 69.1 comes out to, we'll go 3 decimal places, so this is approximately 0.041. And for women, 2.5 divided by 63.6 is about 0.039. Okay, so it looks like men have more height variety, just barely. There's not much of a difference, but relative to their heights, men have a little bit more height variety. They also have more absolute height variety, okay, because their standard deviation, 2.8, is larger than the standard deviation for women, 2.5. But their CV is also slightly larger, so we'll say men have more height variety relative to their average height. Okay, so that's part A. Notice that in part A, we're comparing the groups in total, right? We're comparing all men versus all women. But now part B asks us about specific individuals. It says if Michael Jordan is 76 inches and Tamika Catchings is 75 inches, who is relatively taller? Clearly Michael Jordan is absolutely taller. He's an inch taller than Tamika Catchings. But the question is, does Michael Jordan's height among men exceed Tamika Catchings' height among women? To figure that out, we could either compare their percentile ranks, or we could compare their z-scores. Now, since we don't have any raw data to go off of, we're not going to be able to compute the percentile ranks, but we do have the information that we need in order to compute their z-scores. So let's do that. We'll compute the z-score for each individual. Okay, the z-score is observation minus mean divided by standard deviation. In the case of Michael Jordan, this is going to be 76 because he's 76 inches tall, minus 69.1 because the mean height for men is 69.1 inches, and then divided by 2.8 because the standard deviation height for men is 2.8. And we'll do something similar for Tamika Catchings. We'll say the z-score is x minus mu over sigma. For Tamika Catchings, this would be she's 75 inches tall, minus the average height for women is 63.6 inches. And then we'll divide by the standard deviation for women, which is 2.5. So let's head back over to Desmos and punch these into our calculators and see what we get. So I'll give myself a little fraction. We'll do 76 minus 69.1 divided by 2.8. So there's Michael Jordan's z-score. And then for Tamika Catchings, we'll do 75 minus 63.6 divided by 2.5. So there's her z-score. So it looks like Michael Jordan's z-score is about 2.46, and Tamika Catchings' z-score is exactly 4.56. Okay. So, even though Michael Jordan is taller in absolute terms, in relative terms, Tamika Catchings, I keep saying Hatchings, I don't know why, but in relative terms, Tamika Catchings is much taller than Michael Jordan. Her height among women is much more than Michael Jordan's height among men. Michael Jordan is unusual. He's 2.46 standard deviations above the mean. Remember from the empirical rule, we only expect about 5% of people to be more than 2 standard deviations away from the mean. So that makes Michael Jordan's height pretty unusual. 76 inches is 6'6", so that's, that's pretty unusual. 6'5" for a woman, though, is almost, it's more than 4.5 standard deviations above the mean. That's freakishly tall for a woman, okay? So who's relatively taller? Well, Tamika Catchings, right? Okay, and that will do it for that example. Here's just a table that kind of puts together the tables we have already discussed. So if you want to just describe a data set and give a data profile, these are the measures of center and spread that you should use depending on if you have categorical, skewed, or symmetric data. And then if you want to compare two data sets, then these are the measures of center and spread that you should compare, okay? Again, depending on if you have categorical, skewed, or symmetric data. So this would be a good table to kind of have on hand and kind of memorize. The last page is just a table that I've already posted on Canvas. I don't think I can even zoom out to show you all of the whole thing, so I'll kind of hold my dock cam up so that you can see the whole thing. But this is another good resource that I would keep on hand. Like I said, I've already posted this on Canvas, but I put it here as well just as a summary of the Unit 1 stuff, and it gives you all kinds of good stuff, right? It tells you about the symbols that we use, what they stand for, okay, a description of what they measure, a formula for computing them, right, and then how to compute them in Excel. All right, so that'll do it for our summary of Unit 1. After this, we'll take a test, and then we will move on to Unit 2, which is all about probability.